Good morning, viewer. Vendas here. Here's some breaking news. Methane, a greenhouse gas that contributes significantly to global warming, is also an important source of energy and an essential chemical resource. When used as a chemical feedstock, methane is typically converted into methanol first and then into hydrocarbons. However, this sequential conversion requires complex industrial setups. More importantly, since methane is a very stable molecule, its conversion into methanol requires tremendous amounts of energy when using conventional means such as steam methane reforming. Against this backdrop, the catalytic conversion of methane into methanol or other chemicals has attached much attention from scientists who are eager to find more energy efficient and sustainable solutions. Among recently reported catalysts, copper containing zeolites have shown promises for methane to methanol conversion at mild condition. Unfortunately, the yield and selectivity of most reported catalysts have been low, meaning that large quantities of undesirable byproducts are generated alongside methanol. In a recent study published in Nature Communications, a research team including Associate Professor Toshiyuki Iwaki from Tokyo Institute of Technology, Japan, investigated a new type of bifunctional zeolite catalyst. Interestingly, this copper-containing aluminosilicate-based zeolite is capable of converting methane and nitrous oxide, another greenhouse gas, directly into valuable compounds through a series of intermediate reactions. One of the key questions the researchers addressed was how the spatial distribution of different active sites in catalysts affected the output of the reactions. To this end, they prepared multiply catalysts using not only different concentrations of copper and acid sites proton in aqueous solutions but also different physical mixing techniques for solid samples. Through various experimental and analytical techniques, the researchers found that the proximity between copper and acid sites was crucial for determining the final products. More specifically, they reported that when copper sites were near each other, the methanol produced in copper sites from methane had a higher probability of being over-oxidized by an adjacent copper site, turning it to carbon dioxide. And in contrast, when copper sites and acid sites are close to each other, methanol reacted with nitrous oxide in an adjacent acid site instead to produce valuable hydrocarbons and harmless nitrogen gas. We concluded that for stable and efficient production of methanol and ultimately useful hydrocarbons from methane, it is necessary to uniformly distribute copper sites and acid sites and have them be at an appropriate distance from each other. Explains Iwaki. We also found that the distribution of products obtained is also influenced by the acid properties and pore structure of the zeolite catalyst. One of the most notable advantages of the proposed catalyst is its ability to sustain tandem reactions. That is a simple process that merges multiple steps into one and gets rid of two different harmful greenhouse gases simultaneously. This property will be key to making such catalytic systems attractive in an industrial setting. Benda's exclusive report.